Alright, let's go ahead and take a problem here, and I'm actually going to solve this problem in two different ways. So the first way is an okay way, but it's not actually the point I'm trying to make. So we got the integral from 4 to 9 of the square root of x plus 1, that entire quantity squared, only the x is underneath the radical, and then all of that divided by the square root of x, dx. So one approach we could do for this is to say, hey, this problem's not so bad. Squaring it, I can just use Pascal's triangle 1, 2, 1, foil this puppy out. So basically a perfect squared trinomial. And what this would become would be the integral from 4 to 9 of, so basically a squared plus 2ab plus b squared. So the square root of x squared plus 2 root x plus 1 all over root x. And then what we could do is we could just divide this up into three separate fractions. So we would have x over root x plus 2 root x over root x plus 1 over root x. So I just divided this up into three different parts. And then each one of these parts can reduce pretty nicely because x divided by the square root of x, that's just x to the 1/2 power. And then we go to the next one, we get some nice cancellation going on there. And then the 1 over radical x doesn't really cancel, but I'm just going to go ahead and rewrite that as x to the negative 1/2 power. So writing these with exponents makes it a little bit easier to do the integration. So now we just integrate each piece by piece. So when we integrate x to the 1/2, add 1, divide by the new exponent. So this is all old hat by now. X to the 3/2, dividing by the 3/2, same thing as multiplying by 2/3. Integral of, this is now just a 2, so the integral of 2x. The integral of x to the negative 1/2, and you guys seem to sometimes have issues with this, but when you add 1, negative 1/2 plus 1 becomes 1/2, dividing by 1/2 gives you 2. So, and don't forget, I am evaluating this between 4 and 9. As you guys like to say, we stick it between 4 and 9, because there's the stick. So, this means first you plug in 9, see what you get, and then you got to subtract what you get by plugging in a 4 into all of that. And if you have a calculator handy, you can just go ahead and do this by the calculator. But really, this isn't so bad, because 9 to the 3/2, the 2 on the bottom of the exponent means take the square root. 3 to the 3rd is 27. You can cancel 27 and 3, giving you 9. 9 times 2 is 18, plus another 18, plus 2 times 3 is 6. And we do the same thing with the other side here. So 4... the 1/2 power is 2/3 is 8, so that's 16/3. Oh, that's a little unfortunate, but okay. And you go ahead, you compute this out, 74/3. So, all right. Well, easy peasy, lemon squeezy. But let's go ahead and actually do this in a different way. Let's go ahead and do u-substitution. So, if you're doing this exact same problem with u-substitution, and incidentally, I should point out, if it were just me, I'm doing u-substitution to make a point. If it really was just me left to my own devices, I would just use the wishing game for this. But let's go ahead and use substitution because I want you to see how the bounds change when you do use substitution. So keep in mind right now this is a formula of x's, so this means the x starts at 4, goes to 9, doing the area under the curve of this crazy thing. So let's go ahead and just rewrite this with exponents instead of the radical notation. So integral 4 to 9, x to the 1/2 plus 1 to the power of 2 times x to the negative 1/2. Notice it becomes an x to the negative 1/2 because the square root is the 1/2, but it was on the bottom. So that's the negative part of this exponent right here. So, all right. So if we're going to do u substitution, kind of looks like this should be the u, so we can use the power rule. So let's set it up. U is x to the 1/2 plus 1. Now let's go ahead and see what, by taking the derivative, technically they're differentials, it's not du dx, we're saying derivative of u du is equal to, and just use the regular power rule in the forwards direction for derivative, so fall off the cliff, lose a life, the plus 1 goes away, and by the chain rule, the derivative of the inside, so you have the dx, so 1/2 x to the negative 1/2 dx. Please don't forget this dx, I know that Thresh tends to leave this off a lot, but let's not do that. So one last little thing I want to do here, this will save us having to solve for x and plug it back in like we normally do. So we just kind of say, hey, this is pretty much what we have right here. So let me just go ahead and multiply this over. I'm going to multiply both sides by 2. So we can see that x to the negative 1/2 dx is just 2 du. All right, well, now let's just go ahead and substitute this in. So instead of x's, we're all going to have it in terms of u's. So this is going to be the integral of u squared, because this right here is the u. So u squared. This right here, the x to the negative 1/2 dx, that's just 2 du. So notice this part became this part. Well, what do I do with this 2? It's just a coefficient, so I can pull it outside the integral. So I'm just going to go ahead and do that. Notice I have not put the bounds on here. So a common mistake when you do u-substitution is just to write down the same numbers it was before, 4 and 9. And technically that is incorrect. So, well, more than technically, it's incorrect. So this integral would not be equal to this integral with 4 and 9. So we need different numbers here. And the reason is this was an integral in terms of x. This is a different integral. Right? This is a completely different integral, right? This is the integral of a parabola. This is the integral of u squared to u. This was not a parabola. This was like some crazy thing. I don't even know what this looks like. But this is just saying that whatever this area is between 4 and 9 of this crazy shape, it's just twice the area underneath this parabola. But it's not at the same bounds. It's something else. So to figure out what numbers are going to go here, we have to look back at this original thing. So originally, we had x goes to 4 and goes to x equal 9. So I'm just sort of emphasizing that here. You usually don't write the variable here because we know it from the dx here. But we will need it now in terms of u. So I come over here and I'm going to rewrite and say when x is 4, what would the u actually be? Well, I just go over here, I plug in 4. So 4 to the 1/2 plus 1, 2 plus 1, that's 3. So when the lower bound x is 4, we know that means the u, because we're changing things in terms of u's, is 3. So this 4 is actually going to become a 3. Of course, we still have to figure out what the upper bound is going to be. So before it was x equal 9. When x equals 9, what does that mean u is going to be? So we got to plug x equal 9 into our formula here for u and see what we get. So 9 to the 1/2 plus 1, 3 plus 1 is 4. So hence that means that when x is 9, the u is actually 4. So that's going to be our upper bound over here. So when you do use substitution with a definite integral, there's a little more work you have to do because you actually have to change the bounds to keep it correct. But at least the integral is a lot easier now. So before we had to do crazy foiling stuff with Pascal's triangle, and then we had all kinds of fractional exponents. But here we don't have any of that. The integral of u squared is pretty easy. So add 1, divide by the exponent. So 2/3 u to the 3rd power between 4 and 3. So, and now it's just plugging things in, right? Plug in the 4, plug in the 3, and there you go. It's still the same as it was before. All right, one last problem I just want to take a quick look at, and that's the integral from, say, negative 10 to 10 of sine x cubed dx. So you might wonder, like, what exactly is this function doing? So you can actually kind of reason it out, but let's take a look at the graph first on our calculator. And the reason why I want to do that is most calculators are going to be very misleading as to what this graph looks like. So if we just put in y equals x cubed, y equals the sine of x cubed into your calculator, and let's just do it on Zoom standard. That's negative 10 to 10 for the x and y axis for the window, and you get something that looks like this. So it's just like this crazy random scribble, looks like some baby just scribbled on a piece of paper or something. So, but it turns out the actual graph is something much easier to conceptualize than what the calculator lets you think. So to sort of demonstrate this, I'm going to zoom in a little bit. So if we go ahead and zoom in on that part, let's see what it looks like. So there's more going on than what we first thought, right? If we just go back, it just looks like, some up and down kind of thing, not very much there. But, oh, there's actually a lot more than what we thought. And again, it's still kind of going up and down. Some parts are kind of low, some parts are high, some parts are squished together. But let's zoom in one more time in the center and see what it looks like. Oh, it's a little surprising, maybe. So it's like, hey, it looks just like a sine wave. Now, it turns out it's actually not a sine wave, but it's really close, right? It turns out that each of these cycles is getting slowly closer together and closer together. So, in fact, that's what the entire graph actually is. I'm going to back up here. The only reason it looks so, timey-wimey, wibbly-wobbly is that due to sampling error from the calculator, right? Because there was so much going on, the calculator can only grab so many pixels at a time, so it's just kind of at arbitrary places on the wave. But it turns out this is actually just one nice sine wave where the frequency is increasing as you go along. And if you actually look at the equation, that kind of makes sense, because it's kind of like saying, all right, at the beginning when x is 1, this is sine x. When x is 2, it's kind of acting like sine 4x. Then it's acting like sine 9x. I'm thinking of the x cubed as being x squared in front of an x. So anyway, this is basically a sine wave getting faster and faster and faster as it goes along. It just doesn't look like because the calculator is being goofy. All right, well, how does that help us take the integral? Well, basically the key observation here is that this is an odd function. Well, what does that mean, to be an odd function? So it means that f of negative x is equal to negative f of x, right? So the reason you can kind of see this is odd is, well, we know that x cubed is odd, right? Because when you plug in a negative number, you just get the opposite of the answer you would have gotten if you plugged in the positive version, right? 2 cubed is 8, negative 2 cubed is negative 8. Sine is also an odd function, right? Because I might not know what the sine of negative 8 is, but whatever it is, I know it's just negative the sine of 8, right? So we can use this fact, the fact that we're integrating an odd function, to our advantage. Because if you look at the bounds are going negative 10 to 10. So we can actually sort of split this up and say it's the integral from negative 10 to 0 of sine x cubed dx plus the integral from 0 to 10 of sine x cubed dx. So this next part might seem a little mysterious, but I'm actually going to do u-substitution on this. So just on this first integral. So let's go ahead, I'm going to let u equal negative x, or in other words, that's going to mean that x is going to be equal to negative u, and then dx is going to be equal to negative du, just taking the derivative there. So you might wonder why I'm doing this. Well, it's just to show you why a certain result comes out. So let's go ahead and substitute and replace all the x's with u's in this top one. So notice that when we do this, we have to change the bounds. So before it was x was negative 10. Well, if x is negative 10, that means u is a negative negative 10. In other words, it's 10. Up here, the x was 0. That means u is equal to the opposite of 0. Well, that's still 0. Then we had to replace x with, negative u. So instead of x cubed, it's negative u cubed. And then the dx, we replace that with negative du. So there we go. So there's a little more simplification we can do, but don't forget there's also this part over here. I'm just going to bring that down. I'm not going to substitute the u into that part. I'm just going to keep that part the same. And you'll see why in a minute. So now just a few little easy algebra steps we can do here. So because of the fact that the cubic is an odd function, if I take negative u being cubed, that is negative u cubed. So in other words, I can just pull that negative outside like that. But sine is also odd. So if I do the sine of negative u cubed, I can pull the negative outside there, because that's just negative the sine of u cubed. I'm just using the fact that this is the composition of odd functions. So let me go ahead and pull that negative out. Well, now I've got a negative here and a negative here. I'm going to go ahead and cancel those. And then one other change I'm going to make is over on this integral right here, which I haven't really played with. I'm going to keep it as x's, but I'm going to reverse the order of these bounds. So instead of 0 to 10, I'm going to go 10 to 0, and that changes the sign of the answer. That's one of those integral properties we proved really early on when we were first learning Riemann sums. So I'm going to go ahead and make that change. So, and now for the bit of the leap we need to make here. Think about what this says. This says the integral from 10 to 0 of the function sine u cubed du. That's the area under this curve here. Then we're subtracting the area under the curve from 10 to 0 of sine x cubed dx. Well, this is the same graph, right? The u is a dummy variable, right? So same thing with the x. It doesn't actually do anything. This is just some specific number, and I don't know what this number is, but whatever this number is, I'm subtracting off that same exact number again. This is just the area under the curve from 10 to 0 of sine x cubed. This is the area under the curve from 10 to 0 of sine u cubed. They're the same, right? So when you subtract them, you have to get 0. And again, if you sort of think about it graphically, that totally makes sense, right? Because if you're integrating an odd function graphically just means if you turn it upside down, you get exactly the same thing. In fact, that crazy sine wave graph that was getting faster and faster, this thing, if you turn it upside down, it exactly lands on top of itself, because this is an odd function. So when you integrate any odd function from, negative a number to the positive version of that number, you always have to get 0. This is the mathematical justification of that fact. In reality, when people do this problem, they don't bother to do the substitution and point all this stuff out and split it up. They just say, hey, this is an odd function. Sometimes you actually have to demonstrate mathematically it's odd, but if you're ever integrating an odd function from negative whatever to positive whatever, and those numbers, those whatevers are the same, you have to always get 0.